Okay, so here we are ready for the multiple choice questions and short answer. And number 5, this is a question we've seen before in some form. What type of meter is designed to have as low an electrical resistance as possible? That is the ammeter. The reason being that the ammeter is always put in series with the thing that you want to know the current through. And if you had a big resistance, then you would be changing the current because you'd be putting more resistance in the circuit. Okay? Number 6, what type of field windings on a DC generator results in a higher output voltage for a higher electrical load on the generator? Okay, so that we had a homework question on this type of generator. And when you have this, and you've got sort of this self-excited DC generator, okay, where the field windings are in series with the armature, well, that means that you're going to get a higher output voltage when you have more current flowing through, because when you have more current flowing through a set of windings, you get more magnetic field, and if you have more magnetic field, then you're going to be inducing more voltage onto the armature of your DC generator. So, A is what we want here, okay? Now, 7, electric current in circuits consists typically of electrons. There are electrical circuits that have holes involved at some point. These are essentially virtual particles, quote unquote virtual particles. They act kind of like particles because of the absence of electrons in the valence band of semiconductors, and ions in certain circumstances, like there's ions moving around and creating currents inside of batteries. So like technically that's in there, but generally speaking you're talking about electrons. Oh, hi May. Yeah, you found your box there? Cool. I'm recording a video for my students, so please excuse me. All right. So question 8, transformer must receive AC input to function properly because, okay, we've had a variation of this question as well. Well, A sounds plausible, create a magnetic field, but it's not just a magnetic field, right? It's specifically that we want a changing magnetic flux or a changing number of magnetic field lines in the secondary winding, okay? And we only get that when you have a changing input, so an AC rather than a DC input. So C, secondary winding must experience a constantly changing magnetic field. Yep, that's it. Okay, the rest of them don't qualify. Now, 9, Kirchhoff's loop rule, sometimes referred to as Kirchhoff's voltage law, states that the sum of the voltage drops around a circuit equals the applied voltage difference. Yeah, that sounds pretty good. Let's just check the other ones. Current at every point in a closed circuit loop. No, that's something else. So definitely not that one. Voltage difference is induced. Nope. Then we're sort of testing to make sure that you know about Kirchhoff's loop rule rather than Faraday's law here in C. And then voltage drops across resistors in a circuit loop must be equal. Well, we know that that's not always true, so we can eliminate that one as well. All right. A. Next page is starting with number 10. A fully charged battery with 3 amp hours of capacity will be able to supply a quarter of an amp to a circuit for, okay, well, quarter amp times what equals 3. Okay. So we divide 3 by a quarter and we get 12 hours, right? So it could do 3 amps for 1 hour, it could be 1 amp for 3 hours, and it can do a quarter of an amp for 12 hours, all right? So just testing your knowledge of battery capacity there. Which of the following characteristics are important for a good electromagnet core material? I think we had almost this exact question on a previous exam, so you probably already know the answer to it. Tensile strength is nothing, we never talked about that, and that's not important. Ferromagnetic, yeah, okay, that's important because we want to enhance the magnetic field. And an electromagnet, when we turn off the current, we want the residual magnetism in the core to be low. So we want a soft ferromagnetic material. And paramagnetic is another type of magnetic material, much weaker than a ferromagnet, and so we don't really want that one either. and this one would create a good permanent magnet, but not a good electromagnet core. So A and D. On 12, what happens to a capacitor's, missing my little apostrophe there, apparent resistance, capacitive reactance, when the frequency of the voltage applied to it doubles? Okay, so if we look at the equation for capacitive reactance, okay, we see that when we double the frequency, well, that's going to increase the denominator here by a factor of 2. So that means that the reactance goes down by a factor of 1/2. Okay, so the reactance will be cut in half. C. Okay. What is a clear advantage of an electromagnet compared to a permanent magnet? Okay. Okay, I might have stolen this one actually from this practice exam to put on exam number 2. And it is D, which most of you got on exam number 2, so well done. And all the other ones, it's still made of a bunch of basically metal high-density stuff, so it's definitely not lighter. It may be marginally, but not a big deal. Using electrons is cool, I suppose, but not really important, and there's electrons in permanent magnets too. It's just not formed into a current. Simpler to construct? Probably not. You have to do all those windings, right, for an electromagnet, so I don't think so either. So D. If an AC signal has a frequency of 50 hertz, how long does one cycle of the wave take to complete? Okay, well, remember the relationship between frequency and the period of a cycle of that wave is this relationship. F is equal to 1 over the period. So if we have a 50 hertz frequency, that's equal to 1 over the period. So we flip it, and we get that the period is 0.02 seconds, or 1/50th of a second. And so D is what we want there. All right. All right, on to the second to last page. We've got a couple of light bulb questions here. We didn't really use this symbol for light bulb, but I think it's pretty clear what it's referring to here. Okay. And we're going to answer these 3 questions using this diagram. So which light bulb is brightest? Consider both circuits. Okay, so this actually we need to do a little bit of thinking on, because we want to consider a couple of things. Okay, first, if we started thinking about current, we might come to the conclusion right away that L1 is the brightest, because it is the only light bulb in any of these circuits that receives the total current in the circuit, right? Now the only question is then, okay, well then how does the total current in A compare to the total current in B? And then things get trickier if we're looking at current, because sure, L1 gets all of the current in A, but this L1 is in series with this parallel combination of L2 and L3. So the total resistance here is going to be 1.5 times the resistance of a single bulb. And over here, we're going to have a parallel circuit where we've got the total resistance being actually lower than the resistance of an individual bulb. So the total current over here is actually going to be higher. We can calculate all that out, but I'm not going to. Instead of thinking about current, I'm going to flip over and think about voltage instead, and then the answer becomes clear, because over here, all these bulbs have to split up the voltage applied to the circuit. And because we know that the voltage applied to both of these circuits is going to be the same, okay, because otherwise you couldn't draw these comparisons. Honestly, it should be written out here, though. Okay, voltage applied the same. Okay, there we go. But okay, making that little leap, okay, based on essentially an omission on my part, we know that the entire voltage applied to this circuit is applied across L7. Because it has the same resistance individually as each of these other bulbs, we know that from this form of Watt's law that it must be the brightest one, because it has the largest voltage, has the same resistance as everything else, and so its power being consumed by it and thus turned into light must be biggest. So L 7 is what we're going for there. That's band. Well, I don't know if they're together anymore, but okay. So number 16, which circuit, A or B, has a larger total resistance? Okay, we know from our discussion on the last question that A is going to have a larger total resistance because it's got one light bulb in series followed by a couple of light bulbs in parallel. So its total resistance is 3/2 whatever the resistance of a light bulb is. And over here, we've got 3 in series, but it's in a parallel branch. So we have 3R over 1R. Flip over this whole thing. So we've got 3 over 3R over here, so 4, and then flip. So I think you get 3/4 of the resistance of one bulb. Oops, sorry, I cut that off the video. There you go. Okay. So that one explains number 16. And then 17, which bulbs have the least current flowing through them? Okay. Well, now we're forced to look at the current, aren't we? So, but since we have figured out the answers to 15 and 16 already, and we know that the total resistance of A is 3.5 the individual bulb, or 3/2 times the original bulb resistance, and the other one is 3/4, okay, we can pretty quickly come to some conclusions here. All right. Now, let's take a look. So, current going through A, off the page there, is going to be the voltage applied to A, which is the same for A and B, divided by the total resistance of A, and that's going to be V over 3/2 R. So the expression will look like this. Okay. So 2/3 V over R. Okay, and then for B, the total current looks, similar process. We've got 3/4 R, assuming I did that correctly up there. And when we flip that and write it out, we get 4/3 V over R. Okay, so that's for A. This is for B. And you note that B has exactly twice the total current of A. So that's a nice, clean factor to keep in mind. If we go back up to the diagrams, well, clearly L1 is not going to have the least current, so we can chop that one off, and that takes care of part, or answer B in the last question on this page. And then 2 and 3 are going to get half of the current that's going through the total current, because they're equal resistance, they're in 2 separate branches, so they each get 1/3 V over R. Okay. And then if we go over here to B, pardon me, well, L7 is all by itself in a branch, and it's going to get then, let's see, if you think about this having 3 times the resistance and this having just 1 factor of the resistance, then this branch with 7 in it has to get 3 times the current that's going through all of these guys over here, 4, 5, and 6. So L7 is also not going to be one of the least current ones. And so the question then comes down to, okay, well, how much current is going through 4, 5, and 6? Okay, so if L7 has to have 3 times the current going through it compared to this branch, okay, that means it gets 3/4 of the total current, and this branch gets 1/4 of the total current. If we come down here, 1/4 of this is 1/3 V over R, which is exactly how much was going through L2 and L3, 1/3, so half of this one up here in A, so 1/3 V over R. So 2, 3, 4, 5, and 6, all the ones with check marks, all have tie for the least amount of current going through them, and so we pick D in the last one. So that one was pretty tricky. You might be able to reason it out a different way, but that's the way I went with this time. Okay, last page. We're coming up on the end here. And brushless DC motor is different from brushed DC motors because, okay, it has a permanent magnet on its rotor. Yeah, that's different. And it has electromagnets on the stator. Well, you can have electromagnets on the stator of a brushed DC motor. Let's think about that for a second, because you need to have a magnetic field that the rotor is feeling, and thus making a torque in a brushed DC motor. And so you need to be able to create a magnetic field. You could theoretically have permanent magnets on the stator, but that's not a distinguishing characteristic here. Okay? They both can have electromagnets on the stator. It's just that with brushless, you must. In C, it has a standard commutator, but no brushes. Yeah, that's not going to do it either. Okay, commutators don't work unless you have a brush to connect to it. It has electronics that control the current flowing to the stator so that it can create torque on the rotor. Yeah, so brushed DC motors are very simple. They don't require sort of these control electronics that brushless DC motors do. That's why brushed DC motors were the predominant type of DC motor, or the dominant type, the only type really, until the last several decades, is when brushless came along, when we actually had the control electronics that we would need to do stuff with that. So D, that also is something that distinguishes a brushless DC motor from a brushed DC motor. All right, 19, what is the net charge of a wire that has a current flowing through it? So this one goes all the way back to like the first week of the course. And I think we had this question in a similar form on another assessment somewhere. And the answer is 0, because there are equal numbers of electrons and protons. Because remember, the protons are fixed within the crystalline lattice of a material. It's some fraction of the electrons in conductors that are free to move around, or relatively free to move around. But remember that the current is same everywhere in a circuit if you just have a single path. And so the amount of electrons flowing into one end of the wire and the amount of electrons flowing out of the other end of the wire have to be equal to another, or they'd be building up somewhere and the current wouldn't be the same. So you know that even though there are all these electrons moving, the rate at which they're moving is all the same, and so the total number of electrons and the total number of protons in a particular section of wire are always going to be equal to one another, so they just cancel out to 0 net charge. Interesting, and a little tricky to think about. Okay. All right, last one actually do require a tiny bit of calculation, but pretty short. Draw a circuit that applies a 12-volt difference to one light bulb, applies a 6-volt difference to each of 2 light bulbs, and 3 has a switch connected such that either the 2 6-volt bulbs or the single 12-volt is lit at one time. Okay, so let's say we have a 12-volt battery, all right, and we come out of there and we go to a switch, and let's say it's in that position right now, and we'll put a light bulb there, and we'll come back around to the battery. So if this is a 12-volt battery, then that's one light bulb getting 12 volts difference across it, right? And connected to the other toggle position of this single pole double throw switch, we can have 2 light bulbs in series, like that. In this switch position, there's no completed circuit through those 2 light bulbs, so they won't receive current. And so we're satisfying point number 3 here. And they would each get 6 volts, right? If they're the identical light bulbs, then when the switch comes over here, then they would split the 12 volts 6 and 6, and you're done. So 12 volts there, 6 volts to each of 2, and switch connected so that you can toggle between those 2 configurations. Okay, so 1 bright bulb or 2 dimmer bulbs. All right, and then 21, 6 identical 3-volt batteries that you wish to use to power a light bulb. Draw connections between these batteries such that they produce 6 volts and last 3 times as long as a single battery. Okay, so if you want 6 volts from 3 volt batteries, you have to put at least a couple of them in series, right? So 3 volts, both pushing in current in the same direction, and so they produce a 6 volt difference across the combo. Then you want to last 3 times as long, so what you need to do is take 2 more combinations of these batteries and put them in parallel. A little bit cumbersome to draw, but not too bad. Okay, and then you'd have, whatever circuit resistor or something like that. Okay, so 2 in series, that gets you 6 volts, and then 3 of those combos in parallel with each other, that gets you 3 times as long. And that's the end of the practice final exam, I think. Let's check. Oh, I lied. So, last one. A transformer with a turns ratio of 10 is being used in a circuit. If the RMS voltage difference across the primary is 120 volts, what is the RMS voltage difference across the secondary? Okay, so if the turns ratio, which is this, is equal to 10, so 10 over 1, and that has to equal the ratio of the voltages, and the primary is 120 volts, and we want to know the secondary. So we multiply the secondary to this side, we divide by 10, and that would give us Vs is equal to 12 volts, okay? That should check out, because if we're going down in number of windings, so we're going from 10 to 1, I mean, it might be like 100 to 10 or something, but the ratio is 10 to 1. Well, then we're expecting a step down voltage, and so we're going from 120 to 12, and that checks out. Okay. And for B, if the average power transmitted to the secondary and the primary is 20 watts, okay, so PS is sub S is 20 watts. What is the peak current in the circuit attached to the secondary winding? You may assume the transformer is ideal. Okay, so that if it's ideal, then this equals the power being delivered to the primary, right? So it goes 1 for 1, 20 watts in, 20 watts out of our transformer. And we want to know what the peak current in the circuit attached to the secondary winding is. So we want I peak in the secondary. And let's take a look at that. Well, there's a couple different things we could do to get at this, okay? But we know already that the power being delivered, average power being delivered to the secondary, is equal to the current in the secondary and the voltage in the secondary. And we know that the power in the secondary, delivered to the secondary rather, is 20 watts, and that the voltage RMS across the secondary winding is 12 volts. So this gets us the RMS current. That's the one thing we could screw up here, right? Because we're talking about average power, we're talking about volts RMS, we're going to get current RMS, okay, at that point. Now, if we're looking at that fraction, we get 10 over 6, and so let's see if we can put that in terms of a decimal. So the RMS current is 1.6 repeating amps, and then we just need to use the peak equation, or the peak and RMS relation, to get our peak current. Okay, so we have something like that. And remember that this is just 0.707, or near as makes no difference. So I peak is going to equal I RMS divided by square root of 2 over 2, or 0.707. And if we do that, we get about 2.36 amps is the peak current on the secondary. Okay, so let's check our logic there, and then we'll sign off. We know that 20 watts comes to the secondary. We're asked what the peak current on the secondary winding is. We could use the information that, we could figure out the current on the primary, and then we could figure out the current in the secondary with the current ratio current ratio that we know is equal to the inverse of this voltage ratio. But we can just focus on the secondary here and use Watt's law. And we divide both sides by V. We put in what we know about the average power and the RMS voltage. That gets us RMS current. And then we know that the peak current better be bigger than the RMS current, because the RMS value is like 70% of the peak value, thereabouts. And so when we do that, we do our algebra, we come out to 2.36 amps, equaling the peak on the secondary. And that's that. So, thanks for viewing. Good luck practicing for the final exam. And remember, I have office hours on Sunday afternoon for a couple of hours. Drop in and ask questions.